All right. Well, nice to have most everybody. Okay, so I assume it's Ross's shoe that I see,
Yep.
and I assume no one else is down there.
Yep.
Okay. I should mention that I know at some faculty who teach classes over IVN, whether they are based here in Hattiesburg or down at the coast, will sometimes go to the other campus and then teach from there. And I'm certainly willing to do the same thing on occasion, although it would be nice if more than one of the 3 people down there would show up. So maybe if I announce a date in advance, then that's something to look into. Okay, now all right, so things to talk about before jumping into the usual things. Okay, now, last time I brought up the possibility of a 3/4 of a way take-home test, and in keeping with this class's tradition of putting me in a difficult situation, when I take into account everyone who was here on Thursday to vote yes or no, and anyone else I heard from, like with emailed opinions, the vote, if you will, was dead heat, even split. So like, great. And I don't like being in a situation where I feel like I'm giving approximately half a class a bad deal. So what I've decided to do is, as much as feasible, put both options out there. And so this is a way. Hello, what happened? Okay, this is what I mean by that. Okay, so so each of you have this option. So I've prepared one already, and I'll say more about it in a moment. So what happens in that case is that how your grade is determined is 10%, final 40%. That's true no matter what. Okay, take home 30%, and then homework is remaining 20. And there are, because of deleting a chapter, there are 4 assignments now, each one counting 5%. Okay, now, dang it, stop that. If you do not, and this is something where when I'll talk about dates in a moment, but at the moment I put it out, you'll see the problems, and you can take a look at it and be like, yeah, I can do that, or heck no. And in that case, the first two items are the same. And then homework is 50%, 12.5% each. So you can decide how your how your grade is to be determined. And so what this means is I'm just going to make, so I'm going to figure it out for each one of you individually based on whether you submit the take home or not. So you may take a look at it, maybe even try hand some of them, but if you decide that this isn't the best option for you, but you'd rather take your chances with the homework, and then by then you'll know what all the homework is, because all 4 assignments, then you just don't turn it in. And then your grade is decided the other way. So now, for more information, stop that. I don't know why it puts these question marks. It's really aggravating. Okay. No, stop that. Okay. I'll talk about the Canvas stuff in a moment too. Okay. All right, so I wasn't sure about how much time to give for it, so what I'm going to do is split the difference here. Monday morning, November 6th, due Thursday night, November 9. Okay, and then 6 problems total. Choose any 5. So it'll be 20 points each. Coverage, free on chapter 2. And to be a little more specific about that, relative error, floating point arithmetic issues like cancellation, overflow, that sort of thing. I don't really include anything else from section 2.1, like about condition number or backward error. Relative error comes up, but there's a fair amount of material on various items of floating point arithmetic, such as like cancellation, overflow, like a structure of floating point number, mantissa, like things like that. So there's a fair amount of coverage there. So free problems on that, and then free problems on chapter 6, polynomial interpolation, so Lagrange interpolation, oscillatory interpolation, so that means divide differences play a role, and also, let's see, the error in the polynomial interpolation. So for instance, one thing I'm not covering from chapter 6, there's no problem on there related to Chebyshev polynomials. Okay, but nothing in there about like van der Waals matrices, that sort of thing. So really, 6.2, 6.4, 6.5, those are the sections. Okay, that pop up. Okay, whereas in chapter 2. Little of 2.1, very little, more of a 2.2 on floating point arithmetic. Okay, so that'll give you an idea as to what you're in for, and then so then you can decide when you see it. Are there any questions about this? Okay, so by the time it comes out, you should be hopefully well on your way to finishing. Homework 3. I certainly will have gone over all that material to death, and we'll be into the next chapter by then. But this is like these classes, November 7th and 9th. That's like the exact 3/4 point of the term, or actually no, really, it's the exact halfway point between now and the very end. Okay, so I will update the schedule accordingly. Also, stop it with the dang question marks. Okay. But I think I figured out the trick on how to, maybe. Okay. Okay. Another scheduling note. The final, the regularly scheduled time by the university for a final is on a Tuesday, December 8th, 7th, 6th, December 5th. Homework 4, I'm making due Thursday, December. No, actually, no, that's not true. Friday, December 8th. So basically, it's the last possible day I could accept anything because grades are due Monday the 11th. So as long as if I have something by the 8th, that gives me enough time to grade it, even though I'll actually be attending a conference in Baltimore. Yay. Okay, so just to make sure there's enough time. But of course, you want to try to have as much of homework 4 done before the final, since this material is on the final. But in case you need a little extra time after the final, you can have it. Okay. So I just updated the schedule on that. Okay. I want to talk for a little bit about what I announced the end of last week on. This is actually a suggestion from a colleague about how I can make sure you guys read the stuff in a timely manner. Because I actually thought before the semester started I considered giving reading quizzes because I know Dr. Perry's done that in some of his classes, but I didn't want to give up the class time for something like that. So it was suggested to me, how about giving me a Canvas? Now, so one thing that came up is once I created it, I told Canvas to notify all of you that there's a quiz. And apparently nobody got the notification. Or did anybody get? Okay. And then I found out why. Because also, I was not getting a notification if someone submitted a quiz until first, I started getting notifications when I downloaded the app. So I would not get an email notification. I would get it on my phone. So if you're not sure what's going on with your notifications, so as an example, if you click on your name and go to your account settings and you go to, actually make this a little bigger. Okay, or a lot bigger. So if you click on notifications, come on. So what I discovered was if I go down to, like in my case, I see submissions. And whichever one of these is green is what will happen. So the first column is immediate, then there's daily summary or weekly summary or nothing. And what I found under my email was under submissions, the X was green, meaning don't send me anything. Never tell me if you submit something. Whereas for the app, everything is notified right away. So that's why I was getting notifications that way. So now I just changed it to give me an email notification. And so if you've just submitted like within the last hour or so, like a couple of you did, then I was notified of that. But I also have the app. So I'm finding out 2 different ways, and it's going to really annoy me, but that's okay. Point is, like 7 or 8 of you completed a quiz. So like I said, this is a dry run. So thank you for helping with that. My next question is, for anyone who did not get a perfect score, I would put comments indicating where you went wrong. So, was anyone notified of that in any way? Or this? Okay. No? And that, I don't know if it might be something like this kind of notification is a different notification. I don't know what, I mean, you guys would have different things in here than I would. But that's worth checking. So, if you've submitted the quiz and you don't know how you did, check. And then the next thing I want to know, so I'm going to make a note of this, and I'm going to be reminding you. Check how you did, and if you didn't get 8 out of 8, here's what I need to know this. The intent is, are you able to try again? Are you able to just go ahead and edit your submission and send it back to me? Because I when I created a quiz, I clicked a check. I checked the box for allow multiple attempts. So what I'm hoping is that they make it easy. That you just go ahead, edit, and submit again, and then I take a look at it, and then bump up your score if you got it right. So, but I have no way of knowing. Yes. Oh, it wiped out your answer? Okay. All right, I'm going to try something here. Well, okay. Okay, so what happened for those of you watching a video while I was offline, it was discovered that you can see your attempt and just go ahead and edit it. Okay, so what I'm going to do is, like I said, this was practice for this section, so the due date doesn't really mean anything. But when I post new ones, I'm going to adjust it. I'll probably just give a little more time than what I said because my plan was like write deadline do that class, but I might make it like the next class, something like that. The point is, it's meant to get you looking at the material in a timely manner and put some actual points on the line in a way that doesn't cost class time. Okay. Okay, so this question was answered yes. Okay. And last thing that I mentioned this earlier, check your notification settings. And what I recommend getting the app. Because at least that way, but the default for the app is that you get all the notifications. So you're most likely to be in the know that way. Because when I look at this, when I show you the notifications, like of different things, it's not always clear what refers to what, and you might be thinking you're getting something, and really you're not. Okay, now next item. Okay, before I take any questions on this homework, homework 2, one, I talked about several of these problems last class. One that I believe was not on the list, 2.218, where you're dealing with the expression 1 over 1 minus x minus 1 over 1 plus x, and boy, does that look tacky. I'm going to put that in math mode. Okay. Now, lots can go wrong with this expression. But I'm going to exclude one kind of situation. X equal or nearly equal to plus or minus 1. And the reason is you can see, it's not hard to see that when x is near one of those values that something's going to go wrong with this expression. The trouble is there isn't any straightforward way to fix that just by rewriting the expression. So don't think about that. But what about any other values of x? Possible issues: can anything cause overflow or catastrophic cancellation? And be sure to there's only so many arithmetic operations. We have 2 subtractions, we have an addition, we have 2 divisions. Oh, someone just submitted another quiz. Cool. Or not cool because I had to grade it, but okay. And because any of those are a candidate for something to go wrong. Now for cancellation, of course, that's a subtraction issue, or an addition if the numbers may be of opposite signs. So that's one thing to look for, where it's not as obvious that's a cancellation issue. Okay, and then so keep in mind about cancellation. If it's a situation where I'm going to use different letters here, a minus b, where a is A is approximately equal to B. So what could happen is, the reason why I mention this is, suppose you, the goal is not to get rid of all subtraction. That wouldn't happen anyway, in most cases. But you want to get rid of bad subtraction. So for instance, if you have a subtraction that's problematic because the two numbers being subtracted happen to be really close to one another, and you rewrite it in such a way that whatever subtractions are there do not have that situation, so the numbers are not close, that's good. That will work. So that's why I want to point that out, because when you rewrite the expression, what you're going to get is not devoid of subtraction. It's devoid of bad subtraction for these values of x. So it has to be an apples-to-apples thing, that if you find that for certain x, this expression is bad, you want to rewrite it in such a way that, well, for this same x, it's not a problem anymore. Just like with the one of the other explorations on an exercise on quadratic formula, you have a new way of new quadratic formula, and so you only use it for a situation where it's actually needed, and then for when it's not needed, you use the conventional quadratic formula. Okay, now, are there any other questions about any part of homework 2? So I mentioned more people are getting into the last portion of it, the exercises, which can be kind of a pain, but nothing at all. Yeah.
Since we're doing those Canvas quizzes for the concept checks, do we still need to turn in concept?
No, this is the concept check. Yeah, it's totally taking the place of that. Yeah. Okay. All right. Yeah, so those of you who are, I'm getting multiple submissions here on Canvas, so I will check those as soon as possible after class. Okay, but yeah, as you can see, well, if you're able to get notifications, I'm trying to be Johnny on the spot of these things. But after class, I'm driving down to New Orleans, and tomorrow morning I'm flying to California, but I will keep grading. It's a nice thing about having colleagues in California, then you're still working, but you feel like it's a vacation anyway. Okay, so no questions on homework 2 at this time. Okay. Feel free to shout them out later if they come to you. Talk about today, because the section for today is, well, the ones you just had the concept check on. 6.1 and 6.2, the beginning of polynomial interpolation. So my goal for today is to make sure that there's only a few explorations from these two sections. There's 6 altogether. Should be enough time to give some tips about them, but also there's one part of 6.2 that I never really covered, so I want to take some time to do that. Okay. I can make it a little, okay. All right, so one thing I want to call your attention to when we get to this part where we, the most, I should say, brain-dead way of finding the polynomial that fits given points, solving a system like this one, like the first degree case, or more equations, more unknowns if it's higher degree, that results in this van der Waals matrix. I've added some discussion here that will make one of the concept questions as straightforward as it was supposed to be all along. 6.1 number 3, most people who lost points, actually anybody who lost points at all lost it on that one, I believe. and then there may have been other points lost elsewhere. But so be sure to the textbook is being updated very frequently based on your questions or other feedback. I'm trying to get ahead of you guys on mistakes. So be sure to check that. Like this part here. Okay, next. This one. I did not assign this one. It's a killer. I've gotten multiple questions about it already for people who thought I assigned it when I did not. So just skip over that one. Okay. All right, so I'm gonna make some notes here, so I'll post this later. Okay. Still haven't decided if I want to pay for this program yet. I'm trying to avoid it as long as I can. I think I only have like 20-something days left. Concept check number 3. All right, so check the latest version of the book on that one. Okay, and then explorations in this section are only 3 that I assigned. So in 6.1.3, so there's 2 ways to see, at least 2 ways to see that the interpolating polynomial is unique, no matter how you compute it. One way is related to the van der Waals matrix, so that's discussed in the text. Exploration 6.1.3 has a very different way of seeing that it's unique. So a hint I'm going to give for this one is consider, if we look, I'll pull the problem back up. So it's sort of you can think it's a proof by contradiction. Assume that Pn and Qn are 2 polynomials that fit the exact same data. So same x values, same y values. And you're supposed to prove that these polynomials are, now, you may not be familiar with this symbol, having a equal sign with 3 bars instead of 2. You've seen this before in other contexts, like equivalent to. When we're talking about functions, it has a slightly different meaning. That what we often say is this is, quote, identically equal to. Pn is identically equal to Qn. Sometimes mathematicians will say certain something is identically equal to 0, like a function is. And it doesn't really have any mathematical meaning besides conventional equals. You can think of it as emphasizing that these functions are equal at every single point in the domain. They are exactly the same function, like exactly the same formula. This equivalence is also used sometimes for defining purposes, but here it's just meaning that these functions are exactly the same function, equal at every x. Okay. So if you're assuming that there are 2 such polynomials and you want to show that they're exactly the same, I'd recommend proof by contradiction. So assume Pn and Qn are different, and examine the difference Pn minus Qn, which is also a polynomial, polynomial of degree n, because Pn and Qn are given to be degree n, so certainly their difference would be 2. Okay, so okay, I'm going to give this a name. I'm going to call this Rn. Whoops, I don't want that to be part of a subscript. Okay, this thing's being a pain again. Stop that. Rn. Okay, so what can you say about the roots? Of Rn. So that's kind of your path. Let me fix my spelling mistake here. Okay. All right. Okay. Now, if you have any questions about these, for those of you who've already taken time to look at them, by all means, this is the best time to ask them. So, but otherwise, I'm going to continue going through these in order and seeing what preemptive tips I can give about them. Okay. All right. So, the next one, 614. So this is kind of a way of setting up Lagrant interpolation, because already what we're doing in this problem is we're experimenting with a different way of writing the interpolating polynomial than before. Because at the beginning of a section, we write the first degree polynomial in the most straightforward way that you can imagine. A0 plus A1x. It's power form. It's just what we're all used to. And as the discussion down below says, again, it's a straightforward system to set up, has a nice pattern to it, but it ends up having problems that are discussed down here. So that's why we look at writing the polynomial differently, imposing a different form than this. So for first degree polynomial, we try this form, where we have a constant times x minus x1 plus another constant times x minus x0. So what you will find is if you set up a same kind of system of equations for the unknowns, a0 and a1, then what happens is, okay, so in 614, okay. So what happens here is, in degree 1 case, 2 entries in the matrix are 0, and the key is it is the 2 off-diagonal entries. So you only have 2 coefficients you're solving for in that case, a0 and a1. So the matrix of that system, 2 equations, 2 unknowns, is only going to have 4 entries. Half those entries turn out to be 0, which is something that did not happen when dealing with a van der Waals matrix. But then the problem asks you to generalize to degree 2 case. How can you make all off-diagonal entries, again, equal to 0? So the thing to look at is, in the degree 1 case, what are you doing? You're plugging in x0 and x1 into this. Like you plug in x0, you set it equal to y0. That's your first equation. So let me write that down. So where do my words go? Oh, I went to a new page. Okay. I don't want to have a discussion for problems split across pages. So how the system is set up. For each xi, oh, actually, not xi, for each I, substitute xi into the polynomial, and then what happens is, in this case, one of the terms, we substitute x0 or x1, one of these terms goes away, which causes the system of equations to simplify considerably. And then you set the result equal to the corresponding y value. And you do this for I equals 0 to n. So degree 1 case, you just have two equations, two unknowns, and that happens. And then to get the matrix, once you do that, the entries are whatever is multiplying aj. So in other words, more specifically, the ij entry is whatever is multiplying aj in equation I. And I and j both go from 0 to n. So that's how a matrix comes about. I'm just formalizing what you would have done in Exploration 611. And this is what applies no matter what form of a polynomial you're dealing with. The idea here is you're just trying to get a simpler matrix. So the quadratic case, in setting x equal to xi, you want most of the terms equal to 0. So what form of a polynomial does that? So you think about what made term 0 in the first degree case, you want the same thing to happen in the degree 2 case. It's just that now you're substituting more x values and you have more terms. It's higher degree. Okay. But yeah, the goal is to make most of the entries equal to 0. Okay. So now, related to this problem, but also related to other things I've covered in this chapter. Okay, so I'm going to make a separation here because again, it's not just about this problem, but it is related to it. So what you're used to when it comes to polynomials is you're given a polynomial. Okay, in any math class whatsoever, when you've been given a polynomial, especially low degree, quadratic, cubic, what are you most often asked to do with it? Yeah, factor it. To find what? Find the roots, yeah. So factor it, find the roots. So as an example, like x squared minus 5x plus 6. For some reason, I always use this example. And you factor it to x minus 2. Whoops, I still want to be in math mode. X minus 2, x minus 3. So the roots are 2 and 3. But now, here we're thinking backwards. You're given the roots. Let's see, I need to, let's call them R1, R2, Rn. Get the polynomial. Now, I can draw a parallel here with MATLAB functions. Okay. All right, the roots function is what gives you that. So now you get the polynomial. Which function in MATLAB does that? Anyone? We've seen it, but so no roots, but like you want the coefficients. What? Just poly. Yeah, Polyval plugs in x's. Polyfit does interpolation. Oh, no cheating in polynomial interpolation using polyfit unless the problem says it's okay to use it. Okay, so a valid function in this case is dang it, stop it. Poly. So the polynomial in that case is some coefficient, which I'll call alpha, and then we have x minus r1, x minus r2, and so on. Okay. Now, the reason I bring this up, you might think you're seeing this and like you know this, and you might be like, well, duh. But the point is, there's multiple situations in this chapter where it has to be second nature for you to go from this, like for whatever reason, you know what the roots are, you know what the roots to be, and you have to use the fact that therefore the polynomial has this form, and you work with that form. It comes up in designing Lagrange polynomials. It comes up in seeing why Chebyshev polynomials are so wonderful for reducing error. And the thing is, this might not be instinctive to you to think, oh, okay, I have these roots, but what does that mean? It means this is a form of a polynomial that you can use. So I'm pointing this out explicitly because in the class, like once you get to upper level like this, there are new trains of thought that you need. So when I'm going to try to point these out to you, so you can. But the thing is, ideally, the end goal is for you to make these your own. Now, the way I often phrase it is, you're trying to fill your bag of tricks. So this is one of them. Okay, but yeah, it involves literally thinking backwards from what you're accustomed to. Okay, and alpha can be any non-zero constant. It's not necessarily equal to 1, unless you're given that the polynomial is called a monic polynomial, where the leading coefficient is 1. So like Lagrange polynomials, whatever x values we want it to be 0 at, these are what we fill in here. And then alpha is 1 over all those linear factors that make it equal to 1. Okay. Okay. Now, for Lagrange interpolation, there are certain painful explorations that I chose not to assign. You're welcome. But I still left some doozies for you. So here, after seeing that the most straightforward way of writing a polynomial has its problems, that's in the previous section, here we decide, well, let's just leave this open. Pn is a linear combination of some kind of polynomial here, and as long as they're linearly independent, you can really choose whatever you want and figure out what's most convenient. So in this section, the choice of polynomials that we use are the Lagrange polynomials. And then but we find that has its issues too, even though it's a step up. And in the next section, which I'll cover after fall break, a different choice of phi's are used. Okay, now we've gone over before how you get to Lagrange polynomials. So this is the defining property of them, but you want them to be equal to 1 at a certain point and equal to 0 at all the other x values that are among your interpolation points. And because this is degree n, a degree n polynomial has n plus 1 coefficients. So you have to specify n plus 1 conditions to nail this down uniquely. In fact, I'm going to make a note of that. So stop that. Figure if nothing else while you're suffering through class, maybe my consternation over this program will be mildly amusing to you. Okay. And how great all this is on video. known as the angry numerical analysis teacher. Okay, so a general principle at work here that also comes up in many situations. Matching the number of unknowns, in this case polynomial coefficients, with number of conditions, also described as constraints. So for Lagrange polynomials, they're of degree n. Therefore, need n plus 1 conditions. And those conditions are equal to 1 at one interpolation point, xj, and equal to 0 at n other interpolation points, because you have n plus 1 altogether, xi, for I not equal to j. Okay, bless you. So, and the thing is, normally this would mean like a system of linear equations to find its coefficients, but we already know from a previous section we don't want to take that point of view. That's not practical. But here's where we can use the idea of factorization. These points where it's equal to 0, those are the roots. So here's that factored form that I was just talking about. We multiply these linear factors where these are the roots, and we have some constant out here. We set this constant so that, whoa, no, I did not want a sticky note. Stop that. So that this condition is satisfied, that the polynomial is equal to 1 at the remaining point, xj. Okay. So just emphasizing a thought process that is used to come up with these polynomials in the first place. And why that's so nice is because here, in coming up with a polynomial and a way of writing it, there's two challenges. One is, how do you pick the thighs? Which polynomials do you want to make a linear combination of? Once you decide that, how do you get the coefficients? Well, that's the beauty of Lagrant interpolation. Once you've chosen these to be the Lagrange polynomials, the coefficients, completely trivial. Because what are the coefficients? That's given here. Your y values, or your function values. Those are the coefficients. You don't have to solve for them anything. You just stick them in there. And that's what happens here in this example. Here's my x values, here's my y values. We went through the trouble of getting the Lagrange polynomials before. And once you have them, then right here is you take each Lagrange polynomial and you multiply it by the corresponding y values. 3, minus 4, 5, minus 6. And then you can combine them from there. But as I mentioned, this is still pretty cumbersome because if we add an interpolation point, then we have to redo all this. Also, with Lagrange polynomials written in like this kind of form, zillion subtractions. So what you have to do, perform all these subtractions and then also divisions for each one. And that's not a very efficient way to evaluate a polynomial. I've done a demonstration of this before, like evaluating a polynomial in a standard form, and also Horner's method, and those approaches are way faster than this. We'd like to have a faster way to evaluate the interpolating polynomial once you have it. And that's where the only explorations that I assigned in this section, actually, I want to confirm that. Just number 3 and 4, the ones that relate to barycentric interpolation. And the two explorations center around two formulas that are in this part. So exploration 623, you're computing these values for given x's. So you're writing a function that takes in the input x, which is a vector of your x values, it outputs a vector of the same size that has the weights, wj. So you're just implementing this formula, 6.3, for the x's that you're given. And then the other exploration is to implement this formula. What I'm going to do, though, is, it looks like I'm good on time. I'm just going to take you through this part about what is barycentric interpolation. Actually fairly new phenomenon. It was a lot of numerical analysis that comes up in this class is developed a long time ago. Some of it literally centuries ago before there were computers. It kind of had its heyday like in the 60s. Actually, thanks largely to my PhD advisor and his contemporaries. But this part right here, barycentric interpolation, was actually published in 2004. So, and actually, I happen to know one of the guys who did it, Nick Trefethen, who's at Oxford, England, not Mississippi. And actually, well, he and I are academic brothers. He got his PhD at Stanford too, and one of his advisors was the same as mine. Okay. So the idea is to try to at least plug x values into the interpolating polynomial and get your y values out faster. This is what this technique is for. So what we do is, starting with the form of the Lagrange form of interpolating polynomials. So this is what's developed earlier. But if you go ahead and compute these quantities, so for each j, we take 1 over the difference of xj with all the other x values. So notice in the product here, I'm going for all I values from 0, 1, 2, 3 up to n, but I have to skip j because otherwise, of course, I'd be dividing by 0. Now, at this point, this step doesn't make any sense. Like, well, why would we do that? What is that? How's that helping us? It gives us another way of expressing the Lagrange polynomial that's helpful to us. Because it turns out, I'm going to make a note of this here. Okay, all right. Whoops. Barycentric weights. I'm going to give you an interpretation of them. Because these are actually the denominators of Lagrange polynomials. So we just go ahead and compute those up front. Because no matter what x you're plugging in, that part of Lagrange polynomial is the same. So just go ahead and do that and then reuse it. Okay. And some of you noted on your quiz that this is barycentric interpolation allows you to reuse certain things. Now, what's done here to rewrite the Lagrange polynomial? It's quite tricky, but it's a very common trick. And again, in the interest of enlarging your bag of tricks, I'm going to point it out. Now, first, I'm going to go back to the example that features Lagrange polynomials. Like, suppose we take a look at, here's where I want you to look. Look at this polynomial right here, and this, what I'm highlighting, this form. Focus on the numerator, x minus 0, x minus 1, x minus 2. And then here, we have the next one, x plus 1, x minus 1, x minus 2. And then if you look at the other two, same thing. Again, focus only on the numerators. What do the numerators have in common, and how do they differ? Okay. Sorry, my hearing is awful, so I need you to. Well, okay. Let's focus on these two. Just these two. They both have an x minus 2. Anything else in common? Yeah. So we have two factors in common. Now, if I go to the other two, again, what do they have in common? Yeah, if you pick any two polynomials, in this cubic case, they have two factors in common. Generally, if you have degree n, okay, I can write that down too. So degree n interpolating polynomial is all Lagrange numerators have n minus 1 factors in common. Okay. So here's what's done to rewrite the Lagrange polynomial, because what happens is each one of these is missing one of the factors you have to choose from. What are your factors? X minus each of these. You have 4 factors, you pick any 3 of them. So here's what happens. The way the Lagrange polynomial is written, down here. Here we take all the factors. Don't leave out any of them. And then what's done here? We put that down here, and we divide by the one we don't want. So there's a cancellation. X minus xj is included in this. So we cancel it out, and then we get all the factors that we do want, where we want the x to be the polynomial to be equal to 0 at, and then wj is 1 over our denominator. Actually, I should make that more clear. They are 1 over the denominators of Lagrange polynomials. So that's all we've done here. This is the Lagrange polynomial as you know it. So just to give away the secrets here. So that's what this class is, at least for today, giving away secrets of applied mathematicians. Okay, so the rewritten Lagrange polynomial, all that's done is you multiply and divide by x minus xj. And then you absorb that into the one in the numerator goes into this pi of x. That's a product of all the linear factors. Now, if you're thinking, why? Who cares? What do we have to gain by that? Well, I haven't told you yet. So you just have to hang on. I have 12 minutes. Okay. Actually, that's pi n of x. Keep my notation consistent. Okay. So what we do is we take this form, Lagrange polynomial, and we stick it in here. Now, here's the first part of why this is beautiful and why Trefan is a dang genius. Oh, and his collaborator, I forget his name. I know it's awful of me, but whatever. It's probably a student or something. Okay, so we put this in here, and all the Lagrange polynomials have this pi n of x in common. We factor it out. So, so now we have what's left. No, very simple dependence on x. Just as x minus xj in the denominator in each term. Now, each one of these terms is simple to evaluate. Now, the pi n of x, losing my voice, is still a pain, but we're not done yet. So what happens is, so the purpose to factor pi n out of the polynomial Pn. Okay. So now we've done that. Here's where things get really good. Okay, I'm probably the only nerd in the room who's excited about this, but who cares? It's my class. Now, this is for a general interpolating polynomial. Now let's pick a specific polynomial. 1. Well, how do we get this interpolating polynomial to be equal to 1? That's easy. You just set all the y's equal to 1. So that's what's done down here. We set yj equal to 1. And so that's what we have on the right side, because this is a polynomial of degree n. So a polynomial of degree n that is equal to any specific value, in this case 1, at n plus 1 x's, n plus 1 values of x, is equal to that specific value everywhere. It's only true for polynomials. Okay. Now, if you're not sure about that, if you're not convinced of that, this is related to exploration 6.1.3. So if you go back to that and figure out how that's done, then you'll see why this is true. So in fact, this is actually the exact same situation as in that problem. So here we're dealing with equal to 1. In the exploration, we're dealing with equal to 0. But same principle. So because I've set up a y value is equal to 1, we have n plus 1 points. There's a polynomial degree n. I can say this is equal to 1 for all x. Now, here's a final stroke of genius. Here I have my form of Pn. Here I have my rather complicated form of 1. What do? Divide the equations. What simplification happens? I divide this equation by this one. Too bad across different pages, but let's make that bigger. Okay. So what nice thing happens when I divide these two equations? Yeah, the pi n's cancel. If they're both outside the summation, they're gone. This is all that's left. So here's the, so that's the setup. So the whole point of rewriting that Lagrange polynomial to introduce this pi n of x, the goal was to get rid of it. And we did. So now, this is all that's left. So that's, so the weights, the wj's, those are evaluated up front. Once you have those, then to evaluate a particular x, you would evaluate each of these terms up front. That's n plus 1 evaluate. Well, there's a subtraction and a division. So 2 operations for each. And then you multiply them by the y's to get your numerator. Now, so this is much more efficient. This is a barycentric form that you'll implement in this exploration. Basically, you're writing code that computes this. You use like a for loop, for instance, or the sum function on a vector. Now, there's one wrinkle. 6.2.4. When is the formula that you're supposed to implement, which is equation 6.4, invalid? When is there a problem? Because the thing is, you're given any old x. You're given a vector of x's. When are you going to have a problem with this formula the way it's written? Yeah. So when x equals xj. But suppose x is equal to xj. What's the result of this supposed to be? This is a interpolating polynomial. It's meant to fit given data. So if I plug in xj, forget about this form for a minute. Just focus on this. If I plug x equal xj, what is the expression I'm supposed to get out? It's right here in this mess, but What's the data that I'm given? I'm given xj and what else? Yj. Yes. So, um, the idea is for your x's, whatever x you have here, first check if it's one of your x values. If it is, don't do this. Just don't touch it. Just then the result is a corresponding y value. And otherwise, if x is not one of those, then you go ahead and use this. You know you're not going to divide by 0 in that case. So that's one, admittedly one, you could think of it as a limitation, because it's something you have to watch out for. In fact, this formula is not valid for all x. But at least you know what to do. But in that case, there's no computation needed at all. So that's nice. So with, let's see, Lagrange interpolation versus this barycentric form, both require order n squared operations to evaluate, but barycentric is better because if you think of the number of operations needed as like, when I say big O of n squared, it's a constant times n squared and then plus lower degree terms. But for barycentric, the constant in front of the n squared is smaller. In fact, it can be made almost arbitrarily small depending on how many x's you need to plug in. Just because you compute the barycentric weights once, that's what takes the time. Like, so as far as algorithmic complexity, I'll finish on time today, don't worry. So for Lagrange, n squared. For barycentric, it breaks down into two parts. It's also order n squared to compute the weights, but only order n operations to evaluate at any given x, given the weights. So if you have to evaluate this interpolating polynomial at a zillion x's, then you can think of the cost, the higher cost of computing a weight is kind of like being amortized over all the other work you're doing. So effectively, it could be the more points you need to evaluate at, the greater the advantage of using barycentric. Okay, so I think I hear the sound of people packing up. So, but I've reached the end anyway. So if anyone has any questions about this or homework, but otherwise I'm done. Okay. Or you can stick around after class and ask me then, whatever you need to do. But apparently I have a few quizzes to grade.